In this video, I'd like to talk about the idea of limits of these new kind of functions that we're talking about, the limits of functions of several independent variables. It might be instructive to go back and think about how this went in the first semester. In an informal sense, the statement that the limit as x approaches some real number of f of x equals some real number L just means that if I make x close to c but not equal to c, the difference between f of x and L can be made as small as you'd care to make it. You may or may not be able to make f of x equal L, but that's irrelevant. Someone might give you a positive number, which we're going to call epsilon, and then they could ask you, by making the distance between x and c smaller than some particular amount, can you make the difference between the function value and L smaller than the epsilon that they gave you? That is to say, is there an interval of numbers on the x-axis containing x equals c so that if you're inside that interval, absolute value of f of x minus L is less than epsilon? We keep in mind, of course, we do not calculate what happens at c. So I'd like to know if there's an interval like this where this happens. I'm going to call the horizontal distance from x equals c to the end of my interval, either on the right or on the left, by the letter delta. So putting all of this stuff together that we've talked about, here's the official definition for what it means for this limit to equal L. Given any positive number, epsilon, there needs to exist a delta, which is positive and may depend on the value of epsilon, so that if the distance from x to c is smaller than delta, this keeps me within this interval, and is bigger than 0, that keeps me from looking right at x equals c, then the absolute value of f of x minus L is less than epsilon. This is the actual definition from Calc 1 of what that statement means. To remind you of how dreadful all of this is, let's show that the limit as x approaches 3 of 2x plus 1 is 7 using the epsilon delta argument. I have to look at the difference between my function value, 2x plus 1, and 7. I have to convince myself that there's an interval in which the difference is smaller than any particular positive number epsilon that you might have given me to start with. That is to say, I have to look at the absolute value of 2x plus 1 minus 7, and I have to estimate or express this quantity in terms of the distance between x and 3 on the number line. By doing some algebra, I can re-express this absolute value of function value minus L as being 2 times the absolute value of x minus 3. The reason that this is desirable is the absolute value of x minus 3 is the distance on the number line between x and 3. So my problem is that I want to guarantee that this number, which is equal to this number, is less than epsilon by virtue of making the distance between x and 3 small enough. And I have to tell you what I mean by exactly how small enough. The distance between f of x and L on the y-axis is 2 times the distance between x and 3 on the x-axis. If I want this to be less than epsilon, all I have to do is to restrict the distance to be less than epsilon over 2. There's our delta. If the distance is smaller than delta, then things will work out all right. Now, this is how people actually think about these sort of things. When they write up proofs and stuff, they conceal all of this from you, so I can't resist showing you that, just to show you a bit of irritation at how people do things. I tried doing the smug superior voice, but I really can't pull it off, so I'm just going to say this in my usual way of speaking, but you must imagine that you've got somebody who's all smug and superior and stuff like that. Given epsilon bigger than 0, let delta equal epsilon over 2, which is also positive. Suppose that the distance between x and 3 is less than delta, but positive. We will use this part in our calculation. The absolute value of f of x minus L equals that, which is equal to that, which is equal to 2 times the absolute value of x minus 3, and the absolute value of x minus 3 is less than delta, where delta is epsilon over 2. The absolute value of f of x minus L is less than the number 2 times epsilon divided by 2. This absolute value is less than epsilon. This completes the logical proof. Even in the simplest possible case, doing things with the definition, the epsilon delta definition, is extremely tedious. So very quickly in Calc 1, you found out that you had a bunch of tricks that you could use. There are some functions where to take the limit, all you have to do is plug the number in. Our 2x plus 1 is one of those. There are other limits that you can look at where you can do algebra rearrangements and calculate the limit in some reasonable manner. You also learned things like L'Hopital's rule, so people tend to forget the actual definition of taking a limit is much more complicated than they might remember. It's the one that involves the epsilons and the deltas. All the rest of it is trickery so that we don't actually have to mess directly with those things. Next, I want to think about extending this idea of a limit to functions that have more than one independent variable. For our purposes here today, I'll pretty much stick to 2 independent variables. So I have x and y, which will represent a point in the 2-dimensional plane. I'm going to move that point around and let it get close to the point a comma b, and I want to think in a way that is similar to what we were thinking a moment ago. This statement means this: by making xy sufficiently close to but not equal to ab, I want to guarantee that the function values are close to L. So you see, except for the context, it's the same thing that we had before. I'm going to write down the same definition. Given a positive number epsilon bigger than 0, there's going to be a positive number delta, which may depend on epsilon, so that if the distance from xy to ab is bigger than 0 but smaller than delta, which means I'm close to but not right at a comma b, then the difference between the function value and this L number will be less than epsilon. This is exactly the same idea we had before, except there are two variables in my functions now, and I have to think about this distance business. But that isn't going to be a problem. In the chapter where we first started talking about vectors, we also mentioned, in passing, the distance formula in both 2 and 3 dimensions. We're in the two-dimensional plane as our inputs now, so I'll have a point with x-coordinate A and y-coordinate B. I'll have some other point that I'll just generically call xy. We have previously figured out that the distance between those 2 points is radical x minus a squared plus y minus b squared. So this is the distance that I should write down right there. So this will be my epsilon delta definition for the limit of f of x and y as xy approaches ab to equal L. If I had a function of 3 variables, I would have a plus z minus c squared underneath the radical sign, and my functions would have as their inputs x, y, and z, but otherwise the definition would be unchanged. This is the definition for any number of independent variables. In the one variable case, the distance from the place I'm evaluating my function at to where I'm approaching is between 0 and delta, which means I'm talking about an interval centered at x equals c, but not including it, and you can go as far as delta to the right or delta to the left. The complicating factor to this situation is going to be this. When we go up into 2 variables or more, things are not so simple. If I have a point AB in the plane, and I want to think about all of the places where the distance from AB to point XY is smaller than some number delta, but bigger than 0, the bigger than 0 part just means I don't look right at the point AB. The delta part means the distance is smaller than delta, but it says nothing about which direction I'm in. If I thought about all of the points where the distance were exactly equal to delta, I would have a circle centered at the point AB of radius delta. We want the distance to be smaller than delta, so I do not include this dotted circle in the set of points that I'm thinking about. If the distance were bigger than delta, I would be outside the circle, and if the distance is smaller than delta, I'll be inside the circle. As a result, the thing in 2 independent variables that corresponds to this is not anything as nice as just an interval. You draw a disk, exclude the boundary of the disk, take out the point in the middle, and that's what our set is going to look like. In the one variable case, there's very little variety in the ways that I can get close to x equals c. But in 2 variables, there is literally an unlimited supply of totally different ways that I can get close to the point AB. This, then, is literally going to give us more room for things to go wrong, and life will be harder, in one sense, when we're doing functions of more than one independent variable. As an example, I want to think about the limit as xy approaches 2, 1 of the function 3x plus 5y. This function seems nice enough, so a person might be forgiven for thinking they can just plug the numbers in. In this particular case, that turns out to be right. It certainly seems that it should be like this. This isn't a rigorous argument, though. I have to do the epsilon delta thing in order to do that. So I'm going to look at the difference between the function value and 11 and see if I can't see somehow that by making the distance smaller than some particular number, that I could make the difference between the function value and 11 less than epsilon. What I'm going to do with the 11 is I'm going to break it up into two terms. I'm doing this to try to make the pieces look more like the distance between the 2 points. Because of the triangle inequality, I can split this up some more. Also, in the absolute value, I can factor out an absolute value of 3, which is 3, and in the second, I can factor out absolute value of 5 as well. If I think about how a and b is located relative to x and y, this horizontal part is how different x and a are. The distance across the bottom is the absolute value of x minus a. The vertical distance is the absolute value of y minus b, and the distance between the 2 points is given by the distance formula. If you'll notice, in the distance formula, the quantity underneath the square root is bigger than x minus a squared, so this distance is bigger than radical x minus a squared. This distance is bigger than the absolute value of x minus a. In an exactly similar way, the distance is bigger than absolute value of y minus b. Those two things tell me that x minus a is smaller than or equal to the distance, and so is y minus b. I've got a point xy, I've got another point 2, 1. This is how I'm going to relate this to the distance. So the difference between my function value and 11 is certainly no more than 3 times the distance plus 5 times the distance. The difference between the function value and 11 has absolute value that is certainly no more than 8 times the distance. So if someone were to give me an epsilon that was bigger than 0, and ask, can I produce a delta that's bigger than 0, so that if the 2 points are closer together than delta, produces absolute f of xy minus L less than epsilon, my answer is going to be yes. How small do I have to make the distance in order to guarantee that this number is no more than epsilon, less than epsilon in fact? Given epsilon bigger than 0, let delta equal epsilon divided by 8. Then looking at the difference of the two quantities, the function value and what I think the limit is, that difference is less than or equal to this, and the distance is smaller than delta, where delta is epsilon over 8. The distance being strictly smaller than delta is where I get my strict inequality from. So the difference in the function value and 11 is equal to that, which is no bigger than that, which is equal to that, which is no bigger than that. The difference between the function value and 11 is less than or equal to something, which in turn is less than that quantity, and that quantity is epsilon. If we wanted to do one of these mysterious arguments like we did before, we would say, we will prove this now. Let epsilon be bigger than 0 and let delta be epsilon divided by 8, and then do this calculation, and then I'll find out that f of x and y differs from 11 by no more than epsilon. Even in the simplest possible example, this is kind of difficult to work with. As the functions become more complicated, it becomes more so. Lucky for us, there's a set of facts that we can take advantage of. If we wanted to be strictly logically correct about it, we would have to provide a epsilon delta argument that convinces us that all of the things that I'm about to say are true, but this isn't a proof course primarily, so we won't be doing that anyway. To save writing, in everything that follows, the limit as xy approaches ab of the f function is going to exist at some real number L, and likewise the limit of g exists and is some number m. If I write c, I mean a real number that's a constant. The limit of a constant times a function is the constant times the limit of the function by itself, just like it was in Calculus 1. The limit of the sum of two functions is the sum of the individual limits. The limit of the difference of two functions would be L minus m, the difference of the two functions. Likewise, the limit of the product of two functions can be found by taking the limit of f by itself, the L, the limit of g by itself, the m, and multiplying them together. Similarly, the limit of a fraction of two functions is the limit of the top of the fraction divided by the limit of the bottom of the fraction, provided that the bottom isn't 0, of course.
Of course!
If h is an ordinary Calc 1 type function, then the limit as xy approaches ab of h evaluated at f of x and y is the same as the limit as z approaches L of h evaluated at z. Loosely speaking, f of x and y gets close to L, so however h of f of x and y acts is going to be very similar to how things that look like h of z, where z is a number close to f of x and y, acts. So far, what we know is basically limits act the way that they acted in the first semester. All the usual rules apply to the new situation, but of course we don't know very much about any particular type of functions yet. Some things, though, are pretty clear. If x and y approach a and b respectively, then obviously x by itself approaches a. Likewise, y will approach b. Because of the multiplication rule, the limit of x squared would be a squared, the limit of y cubed would be b cubed, so I can immediately see that I can extend the functions that I know about. Not only that, a function like this will have limits that are easy to evaluate. This would be the limit of x times the limit of x times 4 copies of the limit of y, and we know how those individual limits act. Any positive whole number power of a variable can be treated easily now. The product of such things can be treated easily. If I had several of those things, because of the sum and difference rules, we can deal with those as well. If we wanted to be talky about that, this limit is the limit of that term plus the limit of that term plus the limit of that term, provided that they all three exist. The first term is something that we've already thought about. This term is 3 times x times x times x times y. So because of the product thing, we know how to do the limit of this term. And as y approaches b, an expression of this type where I have terms that are either constants, variables, multiples of variables, or constants times positive whole powers of variables multiplied together. Just like in ordinary algebra, we'll call such a thing a polynomial. With respect to taking limits, polynomials are extremely nice. You literally just plug the numbers in. A ratio of two polynomials will be called a rational function, as you'd expect. The limit as xy approaches ab of x squared plus y squared over 3x squared plus 2y squared plus 1 will be the limit of the top divided by the limit of the bottom, provided that both exist and the one on the bottom isn't 0. Both of those limits will exist because of the polynomial thing. 3x squared is non-negative, so is 2y squared, so the bottom of the fraction is at least 1, so it's never 0. Then, following our previous ideas, the limit is easy to figure out. For this limit, this is one of these h of z situations where the h is the cosine function. As x and y get close to ab, x over x squared plus y squared plus 1 gets close to some particular number, which we don't know the value of. Drawing in the number that I'm going to put into the cosine, a over a squared plus b squared plus 1, on the ordinary calculus 1 graph of the cosine function, there will be a spot of the graph to go with it. Then what I want to think about is it true or false that by making the number that I feed into the cosine close to this number, that I can make the y-coordinates on the cosine graph look a lot like the y-coordinate of that point. The answer is obviously yes. Cosine has the property that you can feed any number into it and get an answer, and you can take the limit as x approaches that number, and you will get the cosine of that value. To use fancy language from Calculus 1, the cosine is continuous every place. This implies that the limit that we're interested in is just the cosine of a over a squared plus b squared plus 1. As my last example, I want to look at that function whose graph was so strange in the previous discussion. F of x and y is going to be the square of the fraction x squared minus y squared over x squared plus y squared. If I think about where this function makes sense, as long as x and y are not both 0, then the denominator will be positive, and the function value will make sense. If x and y are both 0, though, this function value will be undefined. I want to think about the limit as x and y both approach 0 of this function value. It's worth mentioning that if I take the limit as xy approaches some other spot, there's no problem with that. If my point were here, then I can draw a little disk centered at that point, small enough to exclude the origin. The function makes sense everywhere inside that dotted circle. Polynomial upstairs, polynomial downstairs. The downstairs in this disk will never be 0, and then square that. Our short list of rules tells me that the limit of this function as xy approaches this point is easy to figure out. You just plug x equal a and y equal b in, and you're done. That procedure won't work if you're approaching 0, though. No matter how small a disk I draw, centered at the origin, it's going to contain the origin. There's going to be a place where my function is undefined. This tells me nothing, though, about what I'm interested in. Does the limit exist? As an experiment, I'm going to approach the origin by using points on the x-axis. That means I'll be using points where the y-coordinate is exactly 0, so I can simplify the writing of my function values here. If y is 0, my function value is the square of a fraction. The fraction is 0 squared subtracted away from x squared over 0 squared plus x squared. I'm approaching the origin, and the y-coordinate is exactly 0. That means that the x-coordinate is not exactly 0. So when I do this fraction, I end up with 1. So either from the right or from the left, if I approach the origin using only points that are on the x-axis, it looks as though the limit is going to be 1. If I approach the origin using points that are on the y-axis, that means that x will be exactly 0, and that to approach the origin, I'll let the y approach 0. Keeping that in mind, the y is never exactly 0. Upstairs, the negative of y squared. Downstairs, y squared. That fraction is equal to negative 1. Then I square that. Coming in along the x-axis, it looks as though the limit is 1. Coming in along the y-axis, it looks as though the limit is 1. So, obviously, the limit must be 1, right?
Right? Wrong.
Instead, let's approach the origin using points that lie on the straight line y equal x. In my formula for the f of x and y, I'll express this by just writing the y as equaling x. Also, as I approach the origin, I never am really at the origin, so once again, the x in the limit that I'm about to write down is never equal to 0. Since the points that we're using to approach the origin always have x-coordinate different from 0, this function value makes perfect sense. 0 divided by a number that's not 0 is equal to 0, and then if you square that, you get 0 for an answer. So coming in along this pathway, we find that the limit as xy approaches the origin of our function is actually equal to 0. This contradicts what we just said a moment ago. When we approach the origin using points that lie either on the x-axis or the y-axis, the function values that we got all the way in were 1 in both cases, making us think that the limit was 1. But coming in along the straight line y = x, we would think that the limit is 0. By itself, this tells me that there is no single number L that the function values start looking like just because you're close to the origin. If I draw a disk centered at the origin, even if it were 1/1000th of an inch in radius, you're still going to have trouble. At any of the points that I've drawn in with x's here, the function value is going to be exactly 1. This is true if the radius is 1/1000th of an inch, or 1/10000000th of an inch, or however close you want to make it to being at the origin without actually being there. In a similar way, no matter how small this disk that I'm drawing in, there's going to be some points that lie on the line y = x. There's going to be places where the function value is 0. There just isn't any single number L that the function values look like just because I'm close to the origin. In mathematical talk, we say that the indicated limit does not exist. It's unclear just how bad this could get, though, so I want to look at this just a little bit more, and then we'll figure things out. Except for points on the y-axis, which we already know all about, any point is on a straight line that connects it to the origin with slope m. So I'm going to think of selecting some m number, looking at the graph of y = mx, and seeing what happens to my function values as the x approaches 0. As you can see, what I'm going to think the limit is as I travel towards the origin along one of these straight lines is going to depend on what the slope of the line is. So I can get a wide variety of different function values, even though I might be within 1/1000th of an inch of the origin. This reinforces our statement that the limit does not exist. This is about all I'm going to say on the topic of limits. In the next video, which will be rather short, we will discuss the idea of continuity. Then after that, we'll be in a position to start talking about partial derivatives. Until then, I hope everyone's having a good day, and I'll talk to you again soon.